I will give you a short introduction to software-defined radio, so some basics about this technology and some modulation technology, which you also always need if you want to transmit something. So first of all, before we come to the software-defined radio, let's first have a look about what generally happens in a radio transmission, so the parts you always need to get something over the air. So normally you have some input signal, you want to transmit an audio signal, radio for example, a video signal or just any data. Then you do some compression. Mostly you do this if you have some digital stuff. In analog you don't do this so much. You have some error correction, modulation, and then the frequency assignment to the frequency you want to use for the transmission. Then you have a radio channel. Sometimes you have mobility if you move. You have a multipath propagation. You always have some noise added. And often there are also like other signals in the air which also share the channel. And then at the other side, it goes the other way around. You get the demodulation, error correction, if there are errors, and the decompression. And hopefully out comes your original audio or video signal or the data you had transmitted. So a bit to the frequency assignment. There are frequency plans. Here you can see a frequency plan of the US. They had a nice chart like this. Here, for example, you can see the frequency band from 88 to 108 megahertz, then some aeronautical services and other stuff at the other frequencies. For Europe, they have a really huge table. You can find it on the website of the ECO, the European Commission Communications Office. Yeah, it's quite large. But if you want to look what's probably on this frequency in the air, you can have a look there. So now let's start with a not software-defined radio to get a bit more used to the principles, what happens there. Here's, for example, an old AM receiver on this side. So we get the signal in the air, the AM transmission. There are still some, but they are actually switched off at the moment. Here now we have a super heterodyne receiver. It's called like this. So what we have, where's my mouse? Here's my mouse. So we have here at the antenna, here's the antenna, we have our signal S1. That's the signal we want to receive. Then we have some filtering to get rid of all the other signals which are farther away. Then we have our mixer here. So the LO frequency of this mixer, like the local oscillator frequency here, is always chosen in the way that the wanted signal always falls in the same intermediate frequency. That's with this you can have a very sharp filter here, the IF filter. So at your IF filter output you only get the wanted signal, which then after the filtering, again some amplification, goes to the demodulator. And in the case of AM now, all your information is actually in the amplitude of the signal. So for decoding and listening, the easiest way would be just an envelope detector, which could look like this. You have a diode, which actually puts the negative part of the signal to the positive side, and then here we just use a low pass to get rid of the intermediate frequency, which you can still hear, and afterwards you can just listen to your audio signal. So in the case of software-defined radio, we stay to the RX front end in these examples. The TX path would be nearly similar, the other way around. So again, we have the antenna. Antennas are also really important. Always take a good adapted, well-adapted antenna to the frequency you want to receive or the frequency you want to transmit, because otherwise you won't get any signal out of the air, or only a very low part of the signal. I gave a talk on antennas at 31st C3. So if you're interested in antennas, you can have a look on media.ccc.de. Then again, we have some filtering, an amplifier, and now we have an IQ mixer. Here you can see it actually consists of 2 mixers, and this local oscillator signal is shifted by 90 degrees to the lower part here of our signal. Then again, some filtering, amplification, and then we get the analog to digital converters here to get our IQ signal then to the computer for decoding in software. So we still have actually a big analog part here. So most of the front end is still an analog, and the digital part actually is only this after the analog to digital converter, in this case of a classical software-defined radio front end. So IQ data are pretty cool. So they contain actually the raw signal that is coming out of the air. So you could also record the raw signal. It's fastly getting huge. And for example, do then the demodulation later. If you put those IQ signals on a coordinate plane, which you can see here on the right side, you can see also the phase shift between of 90 degrees between the I, which is the in-phase component, and the Q, which is the quadrature component of the signal. If we assign some numbers, we can also combine them with a vector. We can do we can use Pythagoras, for example, to get the amplitude of the resulting vector. We can do some trigonometry to get the angle. And actually, those 2 parameters, like the angle and the amplitude, are the main parameters you can put information in. So in the example before, like the AM modulation, you only use actually the amplitude of the signal. In contrast to this, an FM modulation, for example, has a constant amplitude, and all the information is put to the phase or the frequency. So no matter what kind of modulation is used, this IQ data actually contain all the necessary information. A nice example of a modulation which is often used nowadays, and that also uses both of those parameters, is the QAM modulation. Okay, I already told this. The QAM modulation here, for example, is a constellation diagram out of the program GNU Radio. Oh, it's a bit shifted, everything. Doesn't matter. So here again, we have our in-phase component on the x-axis and the quadrature component on the vertical axis. With the 4 QAM, we have 4 symbols, so we can put in 2 bits per symbol. A 16 QAM, for example, you can put in 4 bits per symbol. If we go further, 64 QAM, we can put in 6 bits per symbol. This, for example, is used in DVB-T or DAB, like broadcasting systems, or in Wi-Fi 802.11n uses up to 64 QAM. LTE also uses up to 64 QAM. When we go farther, 802.11 AC uses 256 QAM, so even more dots. You can put in 8 bits then per symbol, and so does LTE Advanced. And so the more data you want to transmit, the more symbols you need. So 802.11 AX uses up to 10, 1024 QRM with 10 bits per symbol, and so does the successor of 4G, like the 5G new radio, also uses up to 1024 QRM. Becomes interesting when we add some noise. So you always, as I told you, always got the channel, you always got noise. This is what happens if we add some noise to the 64 QRM. You could still like estimate where the original symbol would be. This becomes even more difficult if we go to the 1024 QRM. That's also why those broadband systems always use an adaptive modulation. Like within the first data exchange, they communicate about the quality of the signal, and only if you get a really good signal level at the receiver, you choose the highest order modulation. Otherwise, it is ramped down to lower orders. So this high order modulations only work with really good signal levels. So let's go back to the IQ data. Those IQ data are closely related to complex numbers. So to get a complex number, let's add some imaginary unit j. So we get our complex number actually as c equals I plus j multiplied by q, which are again our in-phase and quadrature component. So complex number are, you can write them in the Cartesian form, which I showed. The mostly often used form is actually the polar form, where we add Euler's number. So it becomes like c equals a multiplied by e, Euler's number, to the power of j phi, which is our phase here again. So in this case, like our real axis, the in-phase axis here becomes our real axis, and the q-axis becomes our imaginary axis. This property of this polar form, which is often needed in digital signal processing, is the multiplication. Like if you multiply two polar formed complex number, this ends up in an addition of the elevated parts here. And this is often used, for example, in Fourier transformations, or if you mix signals to get them from one frequency to the other. More on this later. It looks quite complex, but it's really worth using it at the end. So the first step in the software-defined radio is then to get the right parts of the signal through the front end, because if you don't get your IQ data actually properly, afterwards decoding it in software becomes very, very difficult or even impossible. So let's have a look at the different parts of our software-defined receiver. After the antenna, filtering, and amplifier, we have this IQ mixer. So to keep it a bit more simple, for now we just skip the IQ part and have a look what a mixer in general is doing. To get the signal from the transmitted frequency to the IF, to the intermediate frequency, it is multiplied with an LO signal and then filtered. And this multiplication actually ends up here in an addition, here this higher part, and in a subtraction of the two frequency we put in here. So, and with the filter, we actually get rid of the higher part here. So the mixer defines the frequency range the SDR front end is working on. For example, there are those quite cheap RTL SDR USB sticks which were originally made for DVB-T reception. They work, for example, from 24 megahertz up to 1766 megahertz. Then there is the HackerF, which is also an often used SDR front end, works from 1 megahertz up to 6 gigahertz. And the radio badge from the CCC camp 2015 works from 50 megahertz up to 4 gigahertz. As I told, the mixer here is a bit simplified. Here is, for example, the mixer chipset of the HackRF. Here you can see the IQ mixing part here. Next step then, after again some filtering and amplification, is the analog to digital converter. We get the analog signal in here, and what the computer actually needs are samples of the signal. So they have to be taken at dedicated times, t here, and so we get the sampling rate 1 divided by t. This sampling rate must comply with the Nyquist-Shannon sampling theorem, otherwise your signal can't be reconstructed properly. You get effects like aliasing, where you have frequencies that actually are not there but are caused by the undersampling of the signal. And for complying this Nyquist-Shannon theorem, like the bandwidth of your signal, of the signal you want to digitize, has to be smaller than 1 divided by 2t. Here an example of a DAB plus signal. DAB plus is nice because it always has a bandwidth of 1.5 megahertz. It has quite sharp edges because it uses an OFDM modulation. This here was received with an RTL SDR DAB DVB-T stick with the software GQRX, which has a maximum sampling rate of 3.2 megahertz. So let's check for Nyquist. So we have our bandwidth of 1.5 megahertz. We have the sampling rate of 3.2 megahertz. So 1 divided by 2t is 1.6 megahertz, and 1.5 megahertz is smaller than 1.6 megahertz. So great, we can receive a DAB plus signal with a DAB receiver. You might ask now, this is also for the DVB-T reception, which has a bandwidth of 8 megahertz. So you would need a sampling rate of 60 megahertz to receive or to digitize this. That's actually a nice example of the usage of SDR in comparison to dedicated chipsets. So DVB-T here doesn't use the SDR mode of this chipset, but it has a dedicated DVB-T chipset in here. So chipset development is quite expensive, but if there is a mass market, and for television there is a mass market, they can be produced very cheap. So actually the SDR mode was probably added for the DAB reception. Also, with the growing bandwidth, the power consumption of the SDR mode becomes quite high, because you have always to digitize the whole bandwidth of your signal. So if it comes, for example, to LTE with 20 or 40 megahertz bandwidth, this becomes quite relevant. Okay, we can get the DAB signal here. The next relevant parameter here is the resolution of the ADC. With a 3-bit resolution, for example, you would get 8 discrete values from your signal. With the 8-bit resolution, you get 256 values. With 60-bit, you get a lot of values. And those parts of the step here you can see, for example, the 3-bit resolution and the 16-bit resolution of a sine signal. And all those parts of the steps of the 3-bit resolution actually end up in noise, which is called quantization noise. Here, for example, you see the spectral view of the signal. The first one with a 6-bit resolution, you can see the noise floor here at minus 68 dB. And below, with the 8-bit resolution, the noise floor falls down by 12 dB, so we get a noise floor down at minus 80 dB. What we also see here is actually, here are some examples. The RTL SDR has 2 8-bit ADCs. The HackRF and the radio have a dual 8-bit receive ADCs, and as they are also for transmitting purposes, they have a dual 8-bit, a 10-bit transmit DAC, so the other way around, to get your digital signal in the analog domain again. The RTL SDR is only for receiving purposes. What we also see here is on the right side we get our signal in the time domain. On the left side we get the frequency domain. So how do we get the frequency view of our signal? Here, for example, in the form of a spectral view, and down here is this this with the nice colors. This part is called a waterfall diagram. Here we have the spectrum. In the spectrum view, we see the level of our signal components over the frequency, and the waterfall diagram then shows the different levels in different colors plotted over the time here. So how do we get the frequency view of our signal? Actually, we use a Fourier transformation to convert the time domain signal into the frequency domain. Wikipedia actually had a nice animation about this in public domain. So we have a square wave signal, which is a linear combination of sines of different frequencies, here in blue. And the component frequencies of these sines then are spread across the frequency spectrum, and they are represented here as peaks in the frequency domain. So mathematically, this looks like this. Here we get the different components, the sine components of our square wave signal. For the sake of simplicity, we just skip the harmonics here, just take the sine signal, calculate the Fourier transformation, which is an integral of our function, the sine signal here multiplied by e to the power of minus j 2p ft and integrated over t. We use again the polar form here, which then ends up in a multiplication of this components, and the integral of this multiplication then ends up in delta impulses at a frequency here of a and minus a. And we still have half of an inverse imaginary unit here. If we have a look at the Fourier transform of a complex constant wave signal, this actually simplifies to one delta impulse here at a frequency of a. For practical purposes, computational purposes, we use a DFT, like a discrete Fourier transformation. So the integral ends up in a summation of the signal components. And actually, normally we use a fast Fourier transformation, which you also see in all the software, which is actually an algorithm to efficiently calculate a DFT. So let's have a view again at the DLB signal here with the GQRX software. We have the waterfall view, and because it's a bit small, now here it's actually quite seen. Here it's a bit bigger. So on the left side we have an FFT size of 32,768. And on the right side, an FFT size of 512. And actually, with the FFT length, you define afterwards the resolution of the bandwidth of the spectrum. So you can see here, it's much more coarser than with the higher radio resolution bandwidth here on the left side. Then the sliders down here, you can find those sliders and stuff here in the FTT settings of GQRX. If you want to have a look at this software, the sliders here down, I also have them a bit bigger. Here you can define the reference level. So if you have a very low signal, you have to put it a bit down, and also the range, like the range you see your signal. So if you have a high dynamic signal, you need a large range to see all the parts of the signal. If you have a very, very low signal power, you need to switch it down to a smaller range to actually see anything of your signal. So the possibility is actually to efficiently calculate an FFT or IFFT, like the inverse Fourier transformation, also gave the possibility to a wider use of multi-carrier modulation methods as OFDM here, orthogonal frequency division multiplex. Nowadays, this is often used in mobile communication systems such as LTE due to its resistance to the effects of the propagation channel. For example, multipath propagation often causes destructive interferences. So some of your carriers here actually get are in an destructive interference part. So they are actually attenuated a lot. And if you distribute your information over several carriers, you still have the chance to receive some of the carriers, and then you can afterwards use some error correction mechanisms to repair actually the data and get something out of the data. And so here the FFT, or in the TX case and the transmission case, an inverse FFT is used actually to distribute for example, the QRM data to the different frequencies to the different carriers. Then it's again the regular IQ mixer, and in the case of the reception, we use the FFT to get the symbols, the QRM symbols, for example, out of our different carriers. Here again, you see I like DAB. Again, the DAB signal. Here we have a DAB uses 1,536 subcarriers, and the number of subcarriers here actually is also always a compromise of how close your subcarriers are, which defines how much Doppler shifts in case of mobile reception your system is capable to scope with. And on the other hand, it defines how long your signal is in the air. So the more carrier you have, the longer your signal is. And that has an effect on how much delays your signal can scope with. Additionally, often there is a guard interval added to the symbol, to scope with more delays. For example, DAB is a broadcasting system with the capability of single frequency networks, so you can run different transmitters on the same frequency with the same program, but especially in the overlapping areas, this results in very large delays. So that's why the broadcasting system has very much carriers. LTE, in contrast, only has in the downlink with a 10 megahertz bandwidth 601 carriers, in the uplink 600, and 802.11 AC, for example, with 40 megahertz bandwidth, has 128 carriers. Now let's come back from this quite complex world of software-defined radio to the real world. So what SDR actually brings are quite cheap and flexible solutions of formerly very expensive technology. That's why it's actually often used in academia or also for prototyping purposes. But there's also a quite big community developing open source software for software-defined radio. I want to show you now like 2 examples where those SDR technologies facilitated community-driven projects. One is digital radio, which goes digital in Switzerland, or community radio goes digital in Switzerland. Digitizing local community radios has actually long been a problem. Community radios are non-profit making media produced by a local community and serving a local community. There's also one here in Leipzig, which are also doing a program from the Congress here. I think they are actually starting now for 3 hours today. It's called Fairy Dust FM, so if you want to listen, you can look at the wiki where to receive them. They mostly do not have a huge budget for running a radio. The development was facilitated by low threshold cheap transmitters, so FM transmitters are really cheap now, or they can be built. With DAB now, digital audio broadcast, the possibilities of running your own cheap transmitter became quite difficult for a long time. DAB was developed by the big broadcasting corporations like BBC or the German public media. And it's actually adapted to their needs. You can put in a lot of programs and multiplexes. You can run huge single frequency networks. There's a national SFN in Germany, for example. Local community radios, so does local commercial radios, need more flexible, cheap radio transmission. So you might argue that digital radio isn't relevant anymore, but actually there are countries that start to switch off FM, and only streaming through the internet is also not an appropriate solution. So what happened some years ago was that people started to write open source DAB SDR software to build up quite cheap DAB transmitters. You can find the software here on opendigitalradio.org. They have this nice penguin with a transmission power as a logo. And in Switzerland, the FM switch off is set to 2024. So it's quite coming closer, and a lot of communities are already on the digital airwaves there with this solution of software-defined radio-based transmitter technologies. The UK is also on the way to switch off FM, and there the Ofcom actually recently started a survey about the demand for small-scale DAB, also based on this SDR solution, which makes it affordable to community radios. Another example is community-driven cellular telephony. In In remote areas, for example in Mexico and probably in a lot of more countries, often there is no cellular network connection at all, as it's just not a good business for mobile broadband providers. If you have only a few hundred clients to use it, or customers who pay for it. I was some years ago in the south of Mexico for an article about the first community-driven cellular network, which was also built on open source SDR technology like OpenBSC and OpenBTS, which made it then quite affordable for the communities there. Today, this association, Telecomunicaciones Indígenas Comunitarias, has a license to run autonomous telephone networks in different parts of Mexico, as Chiapas, Veracruz, and Puebla. And nowadays, they are already running nearly 20 cellular networks there. And they also do a lot of trainings and write a lot of manuals. So if you want to learn how to run your own GSM networks, they are actually only, you can have a look on their site. So these are only 2 examples of projects where SDR facilitated low budget communication. So you might ask, if you now want to have a look on SDR yourself, where to start. So for radio reception, this cheap RTL SDR USB sticks are your friend. They cost around 10 to 20 euros, depending on where you get it. There's software like this GQRX, which I already had a lot of examples in my slides, which runs on Linux and Mac. Here is an example of GQRX for FM reception, for example. It has also a built-in FM decoder, so you can really listen to FM radio. There are also AM decoder and some others also. You can also dump the IQ data with this GQRX for decoding it later. There's also software for Windows, like SDR Sharp or HD SDR or WinSDR. Always keep in mind that listening to non-public broadcasts is forbidden. The next level then would be GNU Radio. I already showed in between the talk plots from GNU Radio, like the constellation plots of QAM, modulation. GNU Radio actually offers a very large framework for software-defined radio functions, also to build your own applications. There are sources. For example, here is a source where you can connect your RTL SDR USB stick, define here the sampling rate, the frequency, and different other stuff here. Then you have a lot of function here, for example, the FM demodulation. You have a spectrum here the FFT sync, different resamplers, and then you have different things here. You you can connect it to your sound card with the audio sync, and in this case, listen to FM radio. You can also define a sync to connect your HackRF to transmit something. You can also write your own functions, so it's quite easy in this graphical front end, the GNU Radio companion, to add own functions. There are many tutorials also in the internet, and very active community, and it's also very often used in academia. So if you are perhaps studying or are planning to study, there are very often projects around GNU Radio, which you can work on if you're interested. There's also a lot of different SDR hardware available. So the HackRF I already mentioned, the radio badge from the CCC camp. So if you don't have one, you can ask around, perhaps someone still have one lying around. There are more expensive one, which then have, for example, better resolutions. The DACs have better resolutions. There is the USRP family, which is much more expensive, but you can do a lot more with this, and it's also very often used in academia. I also knew it from my time I worked at the university. So further information, if you are now becoming really interesting, there are lots of massive open online courses. For example, I saw one from the University of Madrid, but in English. So there are video tutorials, for example, from the makers of the HackRF at their website. There are also nice free available books on SDR by Analog Devices, for example, if you look for SDR for engineers. And if you're now here there is an SDR challenge at the Congress. They have a table in Hall 3 in the wastelands there. If we have a look at the small print, so there are various different SDR challenges from quite easy to difficult. There's a game server to claim your flag in a team, and if you don't have an SDR, you can borrow one like this RTL SDR sticks for a deposit. And there are also, if you don't like all this GNU radio stuff, there are also Bluetooth challenges. So thanks for your attention, and feel free to ask questions if you want.
Thank you. We have at least 50 minutes left for Q&A. So walk to a microphone and let's see what you got question-wise. Okay, microphone number 5.
You mentioned that listening to a non-public broadcast is forbidden. What's your basis for this? Because if I recall correctly, the European Convention of Human Rights has an article about being free to conduct journalism, and there was a claim that journalism includes just listening to the entire FM spectrum.
The FM spectrum is public, so there's no problem. But there are other services like that are not encrypted because in former times this technology just wasn't available or affordable for normal persons. So nowadays you have much more possibilities to receive other frequencies, for example, quite easily, which are not public, and so it's forbidden to listen to them actually.
Yeah, but by what? Is there a law?
The law, or I'm not a lawyer, so I don't know exactly what law it is.
Okay.
Okay, any other questions? Does the internet have questions by now? If you have a question, by the way, just walk to a microphone.
The internet doesn't have any questions, but MCR of Open Digital Radio would like to thank you for speaking of them.
Okay, that's not a question.
Sorry, what? I didn't get it.
No questions.
Okay.
Okay, great.
Well, that's a quick one then. Thank you all for your attention. Oh, sorry. Microphone number 2.
It's not a question either. It's just a clarification of the legal situation. So basically, you're allowed to listen to non-public broadcasts or non-public radio traffic for example, like aeronautical, but you're not allowed to record it and to publish the information that you gathered.
Oh, okay, thanks.
So theoretically, sitting at home and listening to, the tower talking to the pilots or whatever, or even to police is allowed. You're just not allowed to, basically make a profit from it. That's the legal situation in Germany. I don't know how it looks in other parts of Europe.
Since we're violating the protocol of Q&A anyway by not asking questions, I am a lawyer, and it varies from member state to member state. You could question whether there's a tension with the European Convention of Human Rights or not, but it really varies from member state to member state.
Well, in that case...
Now I really would like to have a genuine question, something that starts with a sentence and ends with a question mark. Do we have any takers? Oh, in that case, thank you so much for your attention.